the quiz the 282. That is a question about multinomial logistic regression. And we have 5 groups, so 5 classes, A, B, C, D, E. And we have 3 predictors, x1, x2, x3. Then if we use multinomial logistic regression, how many parameters are there? That is the question. And basically, we compare the proportion of the probabilities. So probability of, for example, the y is equal to a as baseline, and that we have to formulate the ratio of the probability of y is equal to a and b, and a and c, a and d, up to probability of y is equal to a and the probability of y is equal to e. So we have to formulate these 4 quantities, y, b over ya, and y, so b over a, c over a, d over a, and e over a. So we have 4 equalities. And in each equality, we have 4 parameters, because we have the coefficient and the coefficient of intercept and coefficient of x1, coefficient of x2 and x3. So 4 parameters. So 4 times 4. So that's why we have 16 parameters. But sorry, the answer, you only have one choice. So anyway, there you got the right answer. Yep. Yeah, so last time that we started the linear discriminant analysis. So linear discriminant analysis is sometimes more stable than logistic regression, because logistic regression is sometimes not stable when the cases are separable. So if separable means the 2 groups are perfectly separated by the straight line, in that case, of course, this categorization problem, categorization, so categorization problem is easier, it should be. But actually, the logistic regression is sometimes unstable because the separating line, we have the infinitely many separating lines. So that makes estimation unstable. But the linear discriminant analysis, the idea is to think about the center of each class. So if the distance between the center of each class is larger, then we have a better discrimination we can get. So it's good for this linearly separable case, at least. Yeah, and I think that was in the quiz, maybe 283. But the basic idea of linear discriminant analysis uses the Bayes rule. So at first, we think about okay, so suppose we have classes, the A, B, C, then we think about probability of some measurement given A. So think about the discriminating the 3 groups, maybe horse, giraffes, and deer. And we think about, for example, the height distribution of deer and height distribution of giraffe and height distribution of horse. And our problem is in the other way. So when we observe the height, we want to see what's the probability that animal is a horse or giraffe. So, but we at first think about the distribution of weight for each animal. So that is more natural, the description of statistics. So probably if you Google it, then maybe you can get the distribution of, so the weight distribution of horse or giraffe or deer. So at first we specify that. Then after that, we use the Bayes rule to translate this into probability of A given X. So given height, we want to see which animal it is. So basically Bayes rule that explains the probability of A given B by the probability of B given A. So by using this formula, that we can identify the probability of Y given X. So to identify, okay, so we observe X, the predictor value, and to identify this, we only need the several quantities. So first, the probability of x given y. So suppose that the observation is in class K, then what's the distribution of x? What's the density function of x? So that is the one information we need. And the other piece of information is the prior probability, unconditional probability. So for example, in some country, how many horses and how many giraffes and how many deers. So that affects our decision. So if most animals in that country are horses, then even if the neck is slightly longer, maybe we judge that animal as a horse. So we need this information, unconditional probability pi k, and the probability of x given y is equal to k. So if we have this information for all animals, then we can calculate this probability. The probability of y is the species, is equal to k given x. X is a measurement such as weight and height. Yeah. And to be specific, linear discriminant analysis uses this normal distribution, so that we assume that this density of x given y is equal to k is this normal distribution, then the probability of this is given by this. So we have used the pi k, so the unconditional probability and the density, the f given k. So this is pi k and the f of k given f of x given k. Yeah. And we discussed the simplest case that k is equal to 2 and the x is one-dimensional. Then what's the threshold? So one class, for example, think about the weight, and suppose the giraffes are heavier than horse, then some threshold we should have. And if the weight of the animal is larger than some point, then we regard that as giraffe, and smaller than horse. And what's the threshold? That is actually the between just the midpoint of two classes. So if the horse has the average weight of 500 pounds and the giraffe has 1,000 pounds, then this point is just the 750. And you can imagine that what will happen when we have multiple predictors and multiple classes. Just separating line or plane or hyperplane is just a flat surface which separates the two groups. Yeah, so this is the case. And the linear discriminant analysis assumes that the variances are the same. And this assumption is useful to make the result stable, because if variances are different, some strange situation happens. So variance is different, often the decision boundary that is more complicated. So in this case, if we compare this density function and this density function, actually here the green density is larger, and also here green density is larger, and in between the purple density is larger. So that is pretty counterintuitive. So if the animal is less than 500 pounds or more than 1,500 pounds, we regard it as a horse, and in between we regard it as a giraffe. That is very counterintuitive rule, and it's not stable, we can imagine. Okay, so anyway, so suppose we are given data. What's the okay, so sorry, let me go back. Yeah, so linear discriminant analysis assume this density function, and our interest is how to estimate this sigma sub k and how to estimate this mu k. And naturally, the mu k is the center parameter for this distribution. So actually, the sample mean is this mu k. So if we estimate the density of measurements given animal, then this mu k is the sample mean of the that specific species. And the sigma k is actually the, a kind of the sample variance that we will see. And actually, the mu k hat, the estimated quantity, is this just the sample mean of the all observations within class k, And the sigma, so remember that the sigma is common for all classes. So we have to take a kind of the weighted average of the squared deviations. And actually, that is true. And we calculate just a deviation for each observation. Then after that, we take summation across all classes. Then we divide by 1 over n minus k. So remember that we estimated the mu1 hat to mu k hat when we have k classes. So we lose the k degrees of freedom. So to make an unbiased estimate, that we have to put the n minus k. So that means the expectation of sigma hat square is equal to the true sigma square. And also expectation of mu k hat is equal to true mu k. So on average, this estimate is correct. So this is pretty simple to calculate. So given classes that we have to calculate at first mu k hat. After you calculate mu k hat, then we can calculate the sigma hat square. So we don't have any complicated procedure. So just we have to calculate a kind of sample means and the sample variance. Then we get all parameters. Then we can decide, we can calculate all the probabilities. So given measurement, we can calculate the probability that the animal is horse, the animal is giraffe, and the animal is deer. So this is kind of convenient. So logistic regression, at least we do some numerical optimization, but here just that we have to use these formulas. So only a few seconds it takes. Yeah, and so far basically we focus on the focus on the univariate case, the predictor. We only have the one predictor, but if we have multiple predictors, just that we regard x as p-dimensional vector, then LDA works in the same way. For example, the mu k is the sample average, but if x is a vector, just sample average for each component, and then we can do it. And here also the deviation square, but you can, if we have two components, that you can see this as the sum of two. So x maybe I1 minus the mu hat k1 square plus the xi2 minus the mu k2 hat square. So just take the norm, the L2 norm. Then you can perfectly follow the same procedure to get the sigma hat square and mu hat k. Yeah, so our assumption is the each f sub k of x follows the multivariate normal distribution. So multivariate normal distribution has this shape. So this is the standard shape. That means that we have the same variance for all predictors, x1 and x2, and we don't have any tilted axis. So just the so I don't know what should I say, but just the density function is given by this shape. Sorry, exponential. And we may have some coefficient. Yeah. And yeah, if we have the relationship between x and x1 and x2, then we should have the different shape. So actually, we have to have some vector x, vector x as x1 and x2, and the mu as mu1, mu2. Then we think about x minus mu transposed the sigma times x minus mu, and sigma usually inverse and exponential, and the 2 pi to the power n over 2. So in this case, actually 2 over 2, so 1. But in general, n-dimensional n over 2, and the sigma to the power n over 2, 1. Oh, sorry, this is also sigma. So this is the density of the bivariate normal distribution, and in general, the multivariate normal distribution. Yeah, so here, yeah, maybe we have to put 1/2, but this is the exact definition of multivariate normal density. So it is an extension of the univariate, the normal, the distribution. And still, we can use almost the same formula to calculate the mu sub k and the sigma. Yeah. So yes, so we define the k sub k, the f sub k of x is here, and our interest is the boundary between the two groups. So given we have data, we have 3 groups. Suppose one group is around here. This is x1 and this is x2. So 2 predictors, and the second group is here, and the third group is here. And what's the boundary? That is our interest. So probably boundary should be like this. And actually, for linear discriminant analysis, these boundaries are all linear, so straight line in case of the 2-dimensional case, and flat plane for 3-dimensional case, x1, x2, x3. So to derive that, basically, we have to solve the f1 of x is equal to f2 of x, or in general, fi of x and f2 of fj of x. So if the densities are equal, then basically we are on the edge. So the probability that observation belongs to class 1 and the probability belongs to class 2 are the same. So that is the boundary between decision boundary between the class 1 and the class 2. So how to equate it? And at first, this part is in common for all cases, so we can ignore it. So then we only have one function, exponential of something. So just take logarithm. So only important part is here. And if we expand this, then that becomes this. So basically the term of x and the term of the x transpose to sigma inverse mu k, and the negative 1/2 times the mu k and something. So we only have these 3 terms. So constant comes from this yellow part. Okay, so this yellow part. Okay. So just we equate the delta 1 of x and the delta 2 of x to find the decision boundary between class 1 and class 2. So suppose this is class 1 and this is class 2. So what's the decision boundary? So maybe if we ignore class 3, then decision boundary is like this, and that will become a straight line. So we would like to show this. So how to do that? So okay, so we equate the delta sub k of x and the delta sub L of x. Then we have this equation. And remember that in the previous page that we have this one, the negative 1/2 times x transpose sigma inverse x. So this is common, the same term for both k and L. So the mu sub k or mu sub L do not matter for the first term. So this term cancel. So only remaining term is important. So we have these two terms on the left-hand side and these two terms on the right-hand side. And you can immediately see that this is a linear function of x. So this is x times some matrix sigma inverse times mu k. Okay, so it's complicated, but at least this is x transposed times some matrix. So this is a linear function of x. And the other the side, it's the same. Okay, so anyway, those are linear functions. And the remaining terms are constant term in terms of x. So that means that this is a linear function of x. That is a straight line for two-dimensional case, or just a flat surface for three-dimensional case. So we can see that the decision boundary is always linear for linear discriminant analysis. So that's why we say linear discriminant analysis. And why this is linear? Because many terms are canceled. Why many terms are canceled? That is because sigma is the same for all k's. You can see that this term, sigma inverse and sigma inverse, if these terms depend on k, then boundary cannot be linear. So we have, suppose this is the sigma k inverse and the sigma k inverse, then we think about the delta L of x, and that is 1/2 times x transpose the sigma L inverse x. Then we have different terms, so it cannot be canceled. So our assumption that sigma is the same for all classes, so that makes boundary linear. Yeah, and you can imagine that if we drop that condition, that we have quadratic term. So the decision boundary is the quadratic curve or quadratic surface. So this is one example. So we have the three classes, and we estimated the f1 of x and f2 of x and f3 of x. So this is the contour plot of f1x. Maybe f1x is equal to some c. And this is contour plot of f2 of x. And this is contour plot of f3 of x. We don't really need a contour plot, but yeah, at least we can see that at this point and this point, the probabilities are the same for the class 1 and the class 3. And in reality, so we know that decision boundary is linear. So this is the decision boundary between the class 1 and the class 3. We continue here, but anyway, so this area is classified as the class 2, so it does not matter. But yeah, so in this way we can make a decision boundary. So at first, so to get f1, f2, f3, we need the mu sub 1, mu sub 2, mu sub 3, and the matrix sigma. And after we estimated that, then we can make decision boundary pretty easily. Yeah, and actually the this sorry, maybe a little different. So sorry, the which is boundary, true boundary is dashed line. Sorry. So in that way that we can get the solid line. Sorry, I thought dashed line is the true boundary, which is the foundation of this simulation. So from the data we get this solid line, and the truth is dashed line. So these two are pretty similar. But of course, this is a pretty good case for linear discriminant analysis because the true boundary is linear. So we already, we have already used that, assumption to model. So the linear discriminant analysis is suitable for this simulation. We know in advance. So that's why it performs well. That is one reason. But at least from the data that we can specify decision boundary pretty accurately. The slight errors, but yeah. Yeah. Okay, so do you have any questions? So these are basically all the explanations for the concept of LDA. Have you used linear discriminant analysis in any of your projects or any of your not personal experience, but anyone has used the linear discriminant analysis in the final project in other classes? Maybe no. Yeah,
no,
so
it's a new subject to me.
Sorry?
It's a new subject to me. I haven't worked
okay, I
with
see.
linear
That's great.
discriminant analysis.
I see. So this class also has our final project. So you have to develop a project and you have to run the analysis. And my suggestion is that you do something beyond the other classes, such as the 50-30. So in 50-30, we did linear regression and logistic regression. So in 58-90, at least I would expect you to do something more than that. So linear discriminant analysis wasn't covered in that course. So this is one good topic. Categorization problem is pretty common, especially for character recognition or some other problems. So I think it's good to pursue it. And for graduate students, hopefully that I would like you to compare different models with reasonable criterion. For example, linear regression and LDA. Linear regression is usually regression problem. So maybe logistic regression and LDA or something like that. Yeah. And the next section, the evaluating classification performance. So yeah, so the regression problem that we can compare the sum of squared errors. So often the rule, maybe RMSE, root mean the sum of the squared errors. So if we estimate y and our estimate is y hat, then we take the difference, maybe usually the yi and our estimate, then take summation and often divide by the sample size and take square root. So this is one good measure for regression. If y is continuous. But how about classification? What rule that should be used? So one is error rate, right? But that isn't sometimes enough. So consider this example. So suppose that there are the 10,000 people for two classes. So default and non-default. So the 10,000 people is classified to either default or no default. So two classes. And the estimated classification, so the estimated classification rule, the misclassified only 275 observation. So basically it's wrong only with 2.75% probability. So this is good prediction rule, the classification rule or not? And to say the answer first, actually, we cannot really say. It depends on the data. Why? So to think about this situation. So in total, we have the 10,000 observations. And this is the predicted default status. We predicted that the 9,896 people are not defaulted. And the only 104 people are predicted as default. And the truth is that we have the 9,667 correct, but the 333, sorry, 9,667 no default, and the 333 people the default. And the and the error rate is actually the 2.75%. So this is error because our prediction and the truth are different. We predicted as yes, but the truth is no. So that is 23 observations, and the other way around, 252 observations. In total, we have 275 observations out of 10,000. So our misclassification rate is 2.75%. It sounds very good, but we are not really sure because, okay, so we think about very easy, we think about the making a very easy decision rule. Just that we predict the no one default. Then what's the graph? What's the table that would be? So we predict all people as the not in default. So that means the table becomes this. So we just predict that no people default. No people are defaulted. So then actually the table becomes this. And how many observations are wrong? How many the predictions are wrong? And actually that's 333 plus 0. So still that we have the 3.33% error rate. So even though that we don't use any information and that we just predicted that all people are not in default, then actually only 3.33% error. So that means the 3.33% is the baseline, and the 2.7% is slightly better than this, but probably not much better. So this example tells us that the error rate itself isn't really the the informative measure to see the prediction performance. Yeah, and also if we use the regression model, so this may be due to the overfitting. So 3.33% to 2.75%, we improved about 0.5% point, but that may be due to overfitting. So if we used all the information and then yeah, so if we have the 10,000 observations beforehand, then we make a regression model. So basically, the situation is that we know the label, so we know which person defaulted. Then we predicted which person will default. So certainly we can do somewhat better than what we can do for the new data set. So even 3.33%, we are not really sure if it's truly a good prediction model, truly useful prediction model or not. Yeah, so we have several problems here. So one is the baseline is actually 3.33%. And another point is we use the data set to make a prediction, and using the same data set, we evaluate the performance. So actually, it's not the practical scheme to measure the error size for new observations. Yeah. And okay, so we will introduce several measures from now on, but at first we just define the several terminologies. So actually, this was the transposed since last table. So this is predicted class, and this is true class. And based on this combination that we define that is true negative. So that means the truth is negative, and sorry, maybe I would say that the predicted is negative, and actually that's the true. So the truth is negative. So true negative. And false negative, predicted as negative, but actually positive. So false negative. So it's the situation that you got the COVID test and the result is negative, but actually you have the COVID. Then that is false negative. And false positive, the predicted as positive, but the truth is negative. So you got the positive COVID test result, but actually the truth is you don't have the virus, then that is false positive. And a true positive, actually that you are tested positive and actually that you have virus, so that is true positive. So we define the TN, the true negative, false negative, and the false positive and true positive. Yeah, so this book assigns also NP as for the truth and N asterisk and P asterisk as predicted. So yeah. And we have several terminologies, the sensitivity and specificity, type 1 error and type 2 error. So how many of you have heard of the sensitivity specificities?
Well, I have heard of sensitivity.
In the usual, the daily life, or in
No, in discrete choice modeling in my master course.
I see, that's great. Yeah. And I think I explained it maybe in 6840, possibly, maybe no. Yeah, so this is often used to measure, especially for diagnostic medicine. So when I first studied these concepts, that is in the book of the statistics in diagnostic medicine. So often the medical doctors explain you about the test result. So you are tested positive, but the sensitivity is here and the specificity is here, or something like that. Okay, so sensitivity is the true positive rate. That is the TP over P. So, okay, so the same graph here. So TP is here, true positive over P. So in total, we have the P true positives, but out of P, we only identified TP. So if the sensitivity is 0.9, that means even if we have the 10 malignant patient, that we can only test positive for 9 people. We can make the test positive for 9 people. So we miss 1 people. And the specificity is the true negative over negative. So that means the true negative, true negative over negative. So suppose we have the 100 the negative, the truly the benign patients, but only out of 100 truly benign patients, we can diagnose only 90 as negative, then specificity is 90%. So sensitivity is usually important because we don't want to miss any malignant cases. So the sensitivity should be high, such as 0.9. Specificity, it depends on the cost of getting the false positive. If false positive isn't really costly, then it's fine. For example, false positive, I don't know, maybe for the case of COVID, maybe you have to quarantine the 2 more weeks or something. If that cost is not too high, then the specificity doesn't have to be very high. So even if specificity is 0.8 or something, it's fine. So sometimes we have we need very high sensitivity, maybe specificity. We don't really have to have very high the specificity, maybe. So it depends on the context. Type 1 error. Type 1 error appeared in most introductory statistics. Type 1 error is the false positive rate. So that is FP over N. So FP, false positive over N. So this is the 1 minus specificity. So lower type 1 error is good. So suppose the true class is negative. What percentage of mistake we make for this negative group? So that is the type 1 error. Type 2 error, the positive, for positive group, how many mistake we make. So usually the type 1 error is the more important. So we want to set type 1 error equal to like 0.05 or something, false negative. Then we set, this is called significance level. Then we make the type 1 error as small as possible. So maybe type 2 error, we have to have very specific threshold. And often the type 1 error maybe a little less important. It depends on the context. But okay, so we defined that these 4 quantities. Actually, we only have to define 2 because 1 minus sensitivity and 1 minus specificity becomes type 1 error and type 2 error. And some other quantities they define, such as Tn over n asterisk or Fp over P asterisk. Yeah, those are relatively the new measures. And yeah, so in the previous table, this is, I think, transposed again, not transposed. Oh, I have already transposed, sorry. So this is predicted and this is truth. So what is the sensitivity? So sensitivity is for the default. Default is positive case in this case, not in default negative. So actually truly positive, and actually we predicted as positive. 81% is the predicted as positive. So 81 over 333. So this sensitivity isn't very high. This is about maybe 0.25 or 24. 0.266 and 1.5, so maybe 2.5, 2.6, I don't know. So it's pretty low. Specificity very high because in total we have 9,667 people in the no default group, and the most people are predicted as that. So actually the specificity is the 0.9. I don't know, 99 something, right? So it's pretty high. So type 1 error is small, so this is less than 0.01. And type 2 error, it's pretty large, 0.74. So we cannot say this is the very good decision rule, but it is somewhat reasonable, because if you compare, proportion of this, I mean ratio of this and ratio of this, at least for default group, that we identify the more consumers as predicted as default. So it's better than nothing. It's better than nothing, but it's not fantastic.
Sorry, Professor.
Yeah.
So for this model, for this prediction that we have made, we can say that our p-value is 0.26, and because of that, this is not a good model. Yes. Model or prediction.
No, I think the significance level and the p-value are different things. So yeah, so we are only doing the description of the test rule. So we are not really thinking about the statistical significance, but the yeah, so we can, yeah, at least we can say that we can only predict 26% of positive cases, so it's not good. But it's not really the p-value. So p-value is given for the data, right? Maybe both are given to the data, but the p-value measures how unlikely our assumption is. So p-value measures how unlikely our assumption is. P-value is small, then our assumption is unlikely. So the p-value is used for that purpose. And here, sensitivity, we only describe the data. So yeah, we can say that 0.26 is low. So it's not the the ideal model, we can say. But yeah, but
better.
I think
it's better not to say in p-value terms.
Right.
Okay.
You're right.
Okay, fine.
Okay, so the next, oh yeah, go ahead.
Yeah, I just had a question about that. Is the reason for that, the model here is actually, or it's actually the boundaries. The boundaries are the model, and then the boundaries help us classify these observations, right? So then the p-values are there p-values on the actual boundaries between classes, or because I understand that this is just like an error rate. Like we're just looking at like what the literal error rate is. So there's no p-value here, but is there a p-value associated with where the boundaries are estimated to be? Oh, sorry, maybe that doesn't, because we are estimating like parameters of the normal, of the multivariate normal distribution in that case. So
yeah, so the to make a decision boundary, you can set the sensitivity first. That is possible. So for example, we can set the sensitivity as 20%.
I see.
Then, yeah, then we get specificity. So basically we have the, yeah, so if we think about making a decision rule, so that will be the next topic. But if we want to make a decision rule, then we have the trade-off between sensitivity and the specificity. So sometimes we set the sensitivity, then we minimize specificity. For example, we set the sensitivity as 30%, then we, maximize specificity given that condition. Sometimes we do that. Yes, but that's right. But that is different from p-value. Yes, but we have certainly the trade-off between sensitivity and the specificity, and sometimes we set we set the number for sensitivity first, then we maximize specificity, or the other way around. That's true.
Got it.
Yeah, so actually now that we think about that kind of problem, so our observation is x, so our predictor is x, and the given x, how to make the decision, so how to judge if the person will be in default or will not be in default. Then one natural way of thinking is the 50% probability as threshold. So probability of default is more than 50% given x, then we regard that person as default. We predict that person will be in default. But that rule is not always the best. For example, the banks want to avoid the risk of having the risky people as the borrowers. So if the default probability is more than 20%, then we want to reject that customer. So in such a situation, we want to set the threshold much lower. For example, some states have restriction on the interest rate. So even if the default probability is 25%, it does not make sense for the bank to lend money to that borrower. So in such a case, we want to set the lower threshold, such as 20%. So in this case, yeah, so we have the different decision boundary. So suppose x is balance of a person, and to predict default status, actually the even lower balance gets slightly higher default probability. So we can predict that person will be in default. So in that way, we can get the other decision rule and the other classification rule and the other error rates, other sensitivity and specificities. And this is the case that we set the default, the probability 0.2 as the threshold. Then the numbers have been changed. So you can see that we have the same number of people which will be in default. So this is the true class, and this is predicted. Then now that we predicted 195 people correctly. So last time only 81, but this time we get much better sensitivity. So actually we have the sensitivity of, I don't know, maybe 60%, almost 60%. Last time only 25%. So if we change that boundary, we can change the sensitivity. But instead, the specificity goes lower. So specificity is this 9,400 over 9,600. So only about 98%. Last time, much more than 99%. So that means that we miss some potential customers. So that is sometimes a bigger issue for the bank. So we have trade-off. We have higher sensitivity, but the lower specificity. So the decision boundary matters for the prediction. So we want to have more, what should I say, the more general the criterion, more comprehensive criterion to see the prediction performance. And that is the ROC curve. So depending on the threshold, the pair of sensitivity and specificity changes. So we plot that. So false positive rate and the true positive rate. So the false positive rate, so that is the 1 minus sensitivity. And true positive rate, that is the true positive, true positive rate is sensitivity, and the false positive rate, this is the truly negative, so 1 minus specificity. So sensitivity and 1 minus specificity as a graph, that is the ROC curve. So since sensitivity and specificity have trade-off, if sensitivity gets larger, then specificity gets lower. So that means the 1 minus specificity gets higher. So this is monotone increasing graph. Okay, and the sensitivity, the 1 is the best. Okay, and specificity, of course, the 1 is the best. So this is the best case. So the good graph is almost along this line like this. And the bad pair of sensitivity and specificity makes this kind of graph. Yeah, and if we do nothing, so that we just make a random rule, then the sensitivity and the 1 minus specificity gets the same. So this is the worst case scenario for the prediction model. So based on this ROC curve, you can see if the area under the ROC curve is larger, so area under this ROC curve, this is larger, then that is a better rule. So that is one possible measure for binary classification problem. And this area is always between 0.5 and 1. So this is called area under the curve. So to be exact, area under the ROC curve. So ROC stands for receiver operating characteristic. So yeah, so use this area to see how good your the decision model is. Then you don't really have to specify the sensitivity or specificity. So you don't have to specify the threshold. So overall, how good your prediction model is, you can see that information from ROC curve and AUC. Questions? Yeah, so ROC curve is more informative, but the AUC is convenient because that is just one number. So if you compare 100 different prediction models, you have to see 100 ROC curves, then it's harder to decide which is the best. But the AUC is a kind of an objective measure for the performance, so that it's convenient. AUC is between 0.5 and 1. And the previous example, AUC was 0.95. So yeah, this also depends on the context. So how difficult the prediction is. So I cannot say which number is the an indication for the good ROC curves, but yeah, but the 0.95, certainly it's a good rule. If it's less than 0.6 or maybe even 0.7, probably it's not very ideal prediction rule. Yeah, so if you use several the models, for example, logistic regression model and linear discriminant analysis for two groups, then suppose you want to compare these two groups, two models, then you have to have some way to compare it. And AUC and ROC curves are a good measures. So you can do analysis by logistic regression. Then you can make the ROC curve and AUC. And the linear discriminant analysis also gives you probability, so you can also construct the AUC and ROC curves. Yeah. I think in the lab session, we will discuss how to make ROC curve in R, also calculate AUC. Questions? How many of you have used ROC curve before?
I have used it for, again, discrete choice modeling.
Discrete choice model. That is
Yes.
in
Transportation.
Transportation. Okay, I see.
Yes.
Yeah, in engineering area, the ROC curve. Yeah, and yeah, diagnostic medicine. Yeah, I see. The transportation. I think that's good. Which college in engineering or?
Well, civil engineering department.
Civil engineering. I see. Yeah, some part of industrial engineering. Yeah. Okay, go ahead.
Yes, we used it for choosing between car and rail transit. Car is 0 and rail transit is 1. It's a binary choice modeling, and we used ROC curve for that.
I see. Yeah. So it's very convenient rule, so that's why it's widely used. And of course, it depends on the case that which is optimal rule or not. Yeah. Yeah. For example, think about the binary prediction problem about the stock market. The stock market is up or down tomorrow. And if you predict it, actually you can predict about maybe almost 60% correctly. That's fantastic, right? So you can, predict the stock market movement, the direction for tomorrow. So it sounds like you can make a lot of money. But that isn't really a good indication for your investment performance, right? So how much it gets higher or how much it gets lower is more important for your performance. So even if you can predict 60% and probably AUC is at similar level, 0.6 or something, but it does not mean that you can get, make money in the stock market. The professor, Lian Fu in economics, she's doing that kind of research, and it's interesting. And at first I heard of it, and okay, so that's funny that we can predict stock market, but actually that does not mean it can make money. So the choice of measure isn't sometimes, the best to achieve some real objectives, such as making money or make people alive or some other the more ultimate goal. Okay, so next one is QDA. So this is similar to LDA, the quadratic discriminant analysis. We drop the assumption that the variance or variance matrix is the same for all classes. So now that we have different sigma k for the different class k. So we assume that the f sub k of x is equal to this. Actually, the log of this f sub k is this. So the exponential of this delta kx is f sub kx. Yeah. So you can easily imagine that this term, so x squared term, does not cancel. So x times this term does not cancel. So the decision boundary becomes quadratic. So that is in some way more flexible. In some way, it's less stable. Yeah. So boundaries are linear for LDA and hyperbolic for QDA. And in terms of bias variance, the QDA is more flexible, but QDA is more complex. So yeah, so basically they're less stable. So variance matrix, the sigma k. So this is, okay, so suppose the predictor X is maybe p dimensional, then this, the sigma sub k is the p by p dimensional. So that is a lot of parameters. So suppose we have 10 predictors, then each sigma k is the 10 by 10 matrix. And this is symmetric matrix. So we have 55 parameters. That is a lot. And if we have, suppose 10 classes, that we have the 55 times 10, so 550 parameters. So estimation is not difficult because we have formula, but you can easily imagine that this isn't really stable for unless sample size is extremely large. Yeah, if you have done any estimation, a statistical model with 550 parameters isn't really good because there are too many parameters, that too much worries for overfitting. So this is the QDA versus LDA. So the dotted line is the decision boundary, the true decision, the purple dashed line is true decision boundary, the simulation that is based on. So purple is the truth. And the black one is the decision boundary by LDA. The green one is decision boundary by the QDA. So you can see that if the true boundary is linear on the right pane, true boundary is linear, then LDA works better. So you can see that this area, LDA is correct, but the QDA is not correct. So almost the LDA is always better. But here on the right pane, the LDA, the QDA is better. The true decision boundary is quadratic. So this one. So if we use LDA, it misspecified the situation, and this part and this part and this part is not correct. But the QDA, it's more reasonable, especially around this area. So it depends on the data. It depends on the underlying truth, whether LDA or QDA is better. Yep. So now that we have more detailed comparison, we have studied logistic regression only for the 2 classes, but we have multinomial version also, and the LDA and QDA and the nearest neighborhood. So nearest neighborhood is more data-oriented, the computational methods, non-parametric methods. So it is based on the k nearest observations to each point. So basically that we make decision based on the majority rule. And the characteristics, both linear regression and LDA have the linear decision boundary. So, but the estimation method is different. So we cannot really simply describe this, but the LDA is better when the case is separable. That is true. But logistic regression is probably better if we have some outliers, because logistic regression is more robust against outliers because of the shape of the function, logistic function. Complexity, nearest neighborhood method with very small k. This is almost arbitrarily flexible. And the LDA and the linear regression, the least flexible, but the more stable. Yeah, logistic regression, not stable for separable case, but otherwise it's pretty stable. And forecasting performance, Yeah, if the boundary is simple, of course, LD and logistic regression is better because we assume the true structure. But if the complicated boundaries, usually the KNN is better than other models. Yeah. So here the simulation result uses two-dimensional predictors. And we have the 6 different scenarios here. So first, first scenario is basically the LDA situation. So LDA is the true. So Gaussian densities with no correlation between x1 and x2. So we generate the data points, the multiple groups based on the simulation rule. So this is exactly the LDA's assumption. So LDA should perform the best. The scenario 2, still the LDA case, but the positive correlation between x1 and x2. So maybe it affects some other models' performance. So scenario 3, T densities with no correlation between x1 and x2. So Gaussian assumption of LDA is violated, so probably logistic regression performs better than LDA. But still, the structure is similar, so logistic regression and LDA perform better than other models. And scenario 4, that we have Gaussian densities with different correlation between x1 and x2 for different groups. So that means if we have, if we have x1 and x2, one group may have negative relationship like this, but the other group have positive relationship like this. So for this situation, so the shape of contour plot is different, so it is better specified by QDA. So QDA should perform better than LDA. And scenario 5, that we have more complicated decision boundary. So Gaussian densities with no correlation for x1 square, x2 square, x1, x2. So basically the truth is in a higher dimensional space. So we cannot represent all structure in the two-dimensional space. So I think it violates both assumption of the LDA, QDA, logistic regression. So possibly non-parametric KNN works better, but still the situation is kind of similar to QDA, maybe. And scenario 6, very complicated rule. It doesn't describe the structure. The textbook does not describe that, but very complicated rule. And the scenario 1 to 2, LDA should be the best. Scenario 3, logistic regression should be the best. So actually the scenario 1 and 2, LDA is best. LDAs are the best. Logistic regression, similar. And scenario 3, actually logistic regression perform better than LDA. And other models, the KNN is not good. KNN is not good. And the QDA is maybe good for this and this, but last one is not good. So this one, really, the Gaussian assumption isn't very good.
Sorry, Professor.
Yeah.
What is the vertical axis? It's error or?
Oh, sorry, the vertical axis error size.
Error size.
Error size. Error rate, maybe. Yeah.
Thanks.
Yeah, sorry. Yeah, and scenario 4, that is the QDA assumption. So QDA is a little more specific situation. So QDA performs much better than others. Yeah, because we assume the true structure. The scenario 5, it's not really clear whether KNN or QDA is better. And the result is, yeah, actually KNN is close to QDA. Or here we have the 2 KNN model. KNN1, that is, one nearest neighborhood. So most flexible, the most overfitted model. KNN, CV. CV stands for cross-validation. So K is optimized for out-of-sample performance. So it's a kind of the best practice for KNN, but still it's worse than QDA because of the underlying data structure. If very complicated rule, then KNN is good. KNN1 is actually worse because this is overfitted. So situation is very complicated. So KNN1 make very complicated decision rule, and that is not good for the out of sample test performance. Yeah, and the QDA is slightly better than this because the QDA can handle more complicated situation than LDA and logistic regression. So the bottom line is it really depends on the data structure. Based on data structure, sometimes logistic model LDA is good. Sometimes the QDA or other models are good. And also, yeah, like scenario 5. So originally we have X1 and X2, but we can make the predictors more comprehensive. For example, we can include X1 square or X2 square or X1, X2, or even higher order terms. Or if you want, you can make any transformation of X1 and X2. Then if we include those variables, then even logistic regression or linear logistic regression or LDA, it can still create a more comprehensive rule. Yeah, so sometimes the KNN or QDA looks better, but if you include enough predictor variables in the model, sometimes this LDA and logistic regression works as good as other models, sometimes even better than other models. Yep. So that is the section, the chapter 4. If you have questions, then you can remain online. And otherwise, see you next week. I will give the homework sometime soon.
Thank you, Professor.